Welcome again in lecture number 6. So these are the topics to be covered. So basically we will begin by introducing transfer learning, a powerful AI technique that has significantly transformed the way we develop machine learning models. So instead of training models from scratch, transfer learning allows us to leverage knowledge from pre-trained models, making AI development faster and more efficient. So what is the meaning of transfer learning? Have you any idea? It is a machine learning technique where a model trained on one task is adapted to perform another, often domain specific task. Instead of starting with an empty model, we reuse knowledge acquired from large datasets and fine tune the model for new challenges. So, what are the purposes behind transfer learning? So, the primary goal of transfer learning is to improve AI efficiency by reducing computational resources, by enhancing performance, by accelerating training, and by common use cases of transfer learning are as the transfer learning has found applications across multiple AI domains, including image recognition, NLP, medical diagnostics, financial forecasting, game changing. So, we can say that transfer learning is a game changing AI technique that helps us build better, faster, and more efficient machine learning models by utilizing existing knowledge. So, throughout this session, we will be exploring out its benefits, applications, and challenges in greater detail. So, traditionally, training deep learning models from scratch requires enormous amounts of data, time, and computational power, as you know. So, however, transfer learning offers a solution by allowing us to reuse pre trained models, reducing development time and resource consumption. For example, suppose instead of training an image recognition model from the ground up, we can take a model like ResNet, which has already learned fundamental image features, and fine tune it for a specific task such as medical image analysis or satellite image classification. So, we can make a comparison with traditional learnings. How? In conventional machine learning, every new problem requires a new model trained entirely from scratch. This means we need large level datasets, extensive processing power, and long training cycles. So, with transfer learning, we start with a pre trained model rather than an empty neural network. Now, again, we require fewer data since the model already has learned features. We use fewer computing resources, making AI more accessible to smaller organizations and researchers. So, what are the key advantages? So, the biggest strength of transfer learning lies in its ability to leverage patterns learned from vast datasets. A model trained on a large data set like ImageNet, which has millions of images, can identify general visual patterns such as edges, shapes, and textures. So, these learned features can then be adapted to new tasks with minimal modifications. This adaptability makes transfer learning particularly useful for domain specific applications where collecting large labeled datasets can be challenging, such as medical diagnostics, natural language processing, financial fraud detection, etc. So, now that we understand the importance of transfer learning, let's explore its key benefits and why it is widely adopted across various industries. So, one of the main concern is faster training time. So, one of the biggest advantages of transfer learning is that it significantly reduces the time needed to train a machine learning model. Instead of training a deep learning model from scratch, which can take days or weeks, we can start with a pre-trained model and fine-tune it for our specific task. And I think you must be clear about what is the meaning of fine-tune that we have learned in previous lecture. So this is particularly used for applications where real-time learning and adaptation are necessary. For example, suppose in computer vision task, using a pre-trained model like ResNet or VGG can reduce training time from several days to just a few hours. Now come to the second point, improved performance. So transfer learning enhances model performance by utilizing pre-trained weights optimized for large data sets. Models trained on the vast datasets such as ImageNet for image classification or BERT for natural language processing already processes generalized knowledge. Fine-tuning these models for a new task leads to higher accuracy and better generalization, especially when labeled data is limited. Now, point 3 is reduces labeled data dependency. So what it means? Many machine learning models require large amounts of labeled data which can be costly and time consuming to collect. So transfer learning allows us to use a pre-trained model that has already learned general features from a different data set, making it easier to train the model even when domain specific label data is scarce. This is particularly useful in medical imaging and rare disease diagnosis, where annotated data sets are limited. Now, point number 4 is applicable across domains. So, under this section, transfer learning is not limited to a single field. It is widely used across various industries like healthcare, finance, robotics, retail and marketing. So you can read all about, you can refer to Google for more information. Now, transfer learning follows a structured process that enables AI models to adapt knowledge from one task to another efficiently. So, the first step is to select a pre-trained model that has been trained on a large dataset. Popular choices includes ResNet, VGG, EfficientNet for computer vision, or BERT, GPT, and T5 for natural language processing. These models already contain learned representations such as detecting shapes in images or understanding sentence structures in text. So once the pre-trained model is selected, the next step is to freeze the initial layers of the model. The lower layers in deep learning models capture generic features like edges in images or basic grammar patterns in text, which remain useful for various tasks. So freezing these layers prevents them from being modified during training, allowing the model to retain its previously learned knowledge. After freezing the base layers, the next step is fine-tuning the model on new domain-specific data. This involves training only the final few layers with new label data to adapt the model to a specialized task. For instance, if we are using a model pre-trained on ImageNet for detecting in chest x-rays, we will fine-tune the last layers with medical images instead of general objects. So finally, the model undergoes evaluation and optimization to ensure high performance. So performance matrices such as accuracy, precision, recall, and F1 score help determine how well the adapted model performs on the new dataset. So we have a basic understanding now of transfer learning. Let's explore the three main types that are commonly used in different applications. So first one is inductive transfer learning, second is transductive transfer learning, and third is unsupervised transfer learning. So we will be discussing one by one. So first one is inducting transfer learning. What it means? This approach applies learned knowledge from a pre-trained model to a related task. The source and the target domains are different, but they share a common feature space. For example, a model trained on general image classification, that is recognizing cats and dogs, can be fine-tuned for a specific task like detecting skin diseases from medical images. In this case, the task changes, but the fundamental learning patterns like edges, shapes, and textures remain useful. Now, second is transductive transfer learning. So, in this type, the source and target tasks are the same, but the domains are different. A great example is training a speech recognition model in English and adapting it to recognize speech in French using domain adaptation techniques. So here the challenge lies in handling domain shift where the new dataset differs from the original one, requiring additional tuning. Now third one is unsupervised transfer learning. So this is useful when no labeled data is available for the target task. And instead of supervised learning, the model learns features in an unsupervised manner and adapts them for a specific application. So a good example is using a model trained on general document clustering and applying it to organize scientific research papers with labeled data. This is becoming increasingly relevant with self-supervised and contrastive learning techniques which enable AI models to learn from vast amounts of unlabeled data. So, a big question is, why is understanding these types important? So, choosing the right transfer learning approach helps optimize AI models for different real-world applications. Some domains require fine-tuning, while others demand domain adaptation. Unsupervised transfer learning is paving the way for AI models that require minimal human labeled data. So now we can discuss one case study, how the transfer learning in healthcare works. So particularly in medical diagnostics. So we just consider a problem of diagnosing pneumonia from chest X-ray images. So one of the major challenges in the healthcare is accurate and timely diagnosis of diseases. So pneumonia, a serious respiratory infection, requires rapid detection to ensure proper treatment. However, traditional diagnostics methods heavily rely on radiologists and manual image analysis, which can be time consuming and prone to human error. So what is the solution? Solution is applying transfer learning with a pre-trained CNN model. To enhance phenomena detection, researchers utilize convolutional neural networks, that is CNNs, such as ResNet 50 pre-trained on large image datasets. By fine-tuning the model with a smaller labeled dataset of X-ray images, the system learns to classify phenomena cases with high accuracy. So, what are the results? The model achieves better accuracy compared to training from scratch, requires fewer labeled images, making it ideal for scenarios where annotated medical data is scarce. So, as we explore the benefits of transfer learning, it's also essential to recognize the challenges associated with this approach. While transfer learning enhances AI model efficiency, its real-world implementation comes with several hurdles. So, first one is domain shift. One of the biggest challenges is domain shift, which occurs when the data distribution in the pre-trained model differs from the target dataset. For example, a medical image classification model trained on X-rays is in one hospital may not perform well in another hospital. due to differences in imaging techniques, equipment, or patient demographics. Addressing domain shift often requires careful data processing and domain adaptation techniques. Second one is overfitting on small datasets. So, overfitting means when fine tuning a pre trained model on a small dataset, there is a risk of overfitting. Means where the model memorizes the new training data rather than generalizing well to unseen data. This happens when too many model parameters are adjusted to fit the smaller dataset, leading to poor performance on real world data. Using regularization methods, dropout techniques, and data augmentation can help mitigate overfitting. Now, third one challenge is computational cost. So, while transfer learning significantly reduces training time, it still requires considerable computational power, especially for large scale fine tuning. Training deep learning models with millions of parameters such as GPT or ResNet demands high-end GPUs or TPUs, which may not be accessible to all organizations. So cloud-based AI services and optimized model architectures can help reduce this burden. Now, fourth challenge is data privacy concerns. So in domains like healthcare and finance, using pre-trained models on sensitive data introduces privacy and security risks. Organizations must ensure compliance with data protection laws, that is GDPR, HIPAA, and adopt secure AI training approaches such as federated learning, where AI models are trained across decentralized devices without sharing raw data. So, as AI and machine learning continue to evolve, transfer learning is also undergoing significant advancements. These trends aim to make AI model more efficient, adaptable, and applicable across multiple domains. So, let's explore some of the most promising trends shaping the future of transfer learning. One is self-supervised learning. So one of the biggest challenge in AI is the need for large amount of labeled data. Self-supervised learning (SSL) helps address this issue by allowing models to learn from vast amounts of unlabeled data. Instead of relying on manual annotations, self-supervised models extract patterns and structures from data itself. For example, OpenAI's GPT models use self-supervised learning to predict missing words in a sentence, enabling them to learn language representations with minimal human supervision. Now, second is meta learning. So, meta learning focuses on training AI models to adapt quickly to new tasks with minimum training data. And instead of training a model for a single task, meta learning enables it to generalize across multiple tasks. For instance, a meta learning model trained on multiple image classification problems can adapt to new categories with just a few examples. Now, third one is cross-domain applications. So currently transfer learning is primarily used within the same domain. For example, a language model trained on medical literature being used for legal document analysis. A computer vision model trained on satellite images being adapted for autonomous vehicle navigation. Now, fourth one is Edge AI. Edge AI and on-device transfer learning models can be optimized to run on local devices such as smartphones, IoT devices, and embedding systems. So this reduces latency, improves privacy, and allows AI to function without an internet connection. For example, AI powered voice assistants like Siri and Google Assistant use on-device models for faster speech recognition. Medical AI tools on Wearable devices can analyze health data in real time without sending information to external servers. So, this concludes today's lecture. Thank you everyone for watching this lecture. If you have any query, you can put your queries on my email ID namitattiwari@csw.ac.in. Thank you so much.